This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome. Have you ever wondered if numbers have hidden patterns? Today, we're exploring Benford's law, a fascinating mathematical phenomenon that reveals how the first digits of numbers in real-world data follow a surprising, counterintuitive pattern. From populations to stock prices, from tax returns to river lengths, this mysterious law appears everywhere. Join us as we uncover why the number 1 appears far more often than you'd expect, and how this discovery helps detect fraud, validate data, and understand the hidden order in our universe. Chapter 1. Discovery in Worn Logarithm Tables. In the reading rooms of late 19th century observatories and mathematics departments, logarithm tables were essential tools of the trade. These thick reference books contained page after page of pre-calculated logarithmic values, sparing scientists and mathematicians from tedious hand calculations. Before the age of calculators and computers, anyone needing to perform complex multiplication or division would reach for these well-thumbed volumes, find the relevant logarithms, add or subtract them as needed, and then convert the result back using anti-logarithm tables. In 1881, a Canadian-American astronomer named Simon Newcomb made an observation that would have escaped the notice of almost anyone else. As he reached for his logarithm tables one day, Newcomb noticed something peculiar about the physical condition of the book. The pages weren't wearing evenly. The earliest pages, those containing logarithms of numbers beginning with 1, showed considerably more wear and tear than the middle pages. The pages grew progressively cleaner and crisper as he flipped toward the back of the book, where the logarithms of numbers beginning with 8 and 9 resided. To most people, this would have been a curiosity barely worth a second thought. Perhaps the book had been bound improperly, or maybe the pages at the front were made of inferior paper. But Newcomb possessed the kind of mind that sees significance in small details. If the front pages of logarithm tables were more worn than the back pages, it meant his colleagues were looking up logarithms of numbers beginning with 1 far more frequently than those beginning with 9. This wasn't a quirk of a single book or a single library. This was a pattern that revealed something fundamental about the numbers scientists and mathematicians actually worked with in their daily research. Newcomb reasoned through the implications. Logarithm tables weren't fiction. They were used to solve real problems involving real quantities from the natural world. If astronomers, physicists, and engineers were consulting logarithms beginning with 1 more often than those beginning with 9, it meant the actual numbers they encountered in their work, be they distances to stars, masses of celestial bodies, or measurements of physical phenomena, more frequently began with the digit 1 than with 9. The wear pattern on these reference books was a physical record of an underlying mathematical truth about naturally occurring numbers. That same year, Newcomb published his finding in the American Journal of Mathematics in a brief article titled, "Note on the Frequency of Use of the Different Digits in Natural Numbers." His paper opened with a straightforward observation. That the 10 digits do not occur with equal frequency must be evident to anyone making much use of logarithmic tables, and noticing how much faster the first pages wear out than the last ones. The first significant figure is oftener 1 than any other digit, and the frequency diminishes up to 9. Newcomb didn't stop at merely noting the phenomenon. He quantified it. He proposed that in naturally occurring numbers, the probability that a number begins with a particular digit could be calculated using logarithms. Specifically, he stated that all mantissae of logarithms are equally probable. The mantissa is the fractional part of a logarithm, and if these are uniformly distributed, then the probability of observing a first digit d follows a precise mathematical formula, the logarithm of 1 plus 1 divided by d.
This seemingly abstract statement had concrete implications. It meant that approximately 30% of naturally occurring numbers should begin with the digit 1, while less than 5% should begin with the digit 9.
Newcomb even provided a detailed table showing the expected frequencies not just for first digits, but for second digits as well. According to his calculations, the digit 1 should appear as the first digit 30.1% of the time. The digit 2 should appear 17.6% of the time. Each subsequent digit from 3 through 9 should appear with steadily decreasing frequency, with 9 appearing as the first digit only 4.6% of the time. For second digits, which include 0, the distribution was more gradual, but still not uniform. 0 should appear as the second digit nearly 12% of the time, while 9 should appear less than 9% of the time. What made Newcomb's observation so counterintuitive was that it violated basic expectations about randomness. If someone asked you to guess the first digit of a randomly selected number, you might reasonably assume each digit from 1 through 9 has an equal chance of appearing. After all, why should one digit be inherently more probable than another? Yet Newcomb's worn logarithm tables told a different story, one where lower digits dominated and higher digits receded. Newcomb's paper made another crucial observation about the nature of these numbers. He noted that in examining natural numbers, we must consider them as ratios of quantities. A population isn't just an abstract number, it's a ratio of people to a unit of counting. A distance isn't merely a figure, it's a ratio of space to a unit of measurement. This insight hinted at a deeper truth. The distribution of first digits might be connected to fundamental properties of measurement and scale rather than to any particular physical phenomenon. Despite the elegance of Newcomb's discovery, his paper generated little attention at the time. It appeared, sparked no controversy or extensive follow-up research, and then faded into obscurity. The mathematical community moved on to other problems. For more than 50 years, Newcomb's observation about the unequal distribution of leading digits languished, unread and unremembered, in the archives of academic journals. Then, in 1938, a physicist named Frank Benford, working at the General Electric Company, made the same discovery entirely independently. Like Newcomb before him, Benford noticed that the pages at the beginning of logarithm tables showed more wear than those at the end. Unlike Newcomb, Benford decided to investigate the phenomenon extensively and systematically. He embarked on an ambitious project to test whether this pattern held across wildly different types of data. Benford compiled an enormous data set consisting of 20,229 observations drawn from 20 different sources. The diversity of his data collection was remarkable. He examined the surface areas of 335 rivers, gathering measurements of watersheds and drainage basins from around the world. He compiled the sizes of 3,259 populations of towns and cities across the United States. He collected 104 physical constants from physics and chemistry, those fundamental numbers that describe the behavior of the universe, from the speed of light to the mass of an electron. He gathered 1,800 molecular weights of chemical compounds. He pulled 5,000 entries from a mathematical handbook. He even went so far to extract 308 numbers from a single issue of Reader's Digest magazine, collecting every number mentioned in the articles. He recorded the street addresses of the first 342 persons listed in American Men of Science. He compiled 418 death rates from various causes and locations. The breadth of Benford's investigation was its strength. River areas have nothing inherent in common with molecular weights. Population sizes share no obvious connection with death rates. Street addresses follow completely different generation processes than physical constants. Yet when Benford tabulated the first digits of all these diverse numbers, he found the same pattern emerging again and again. Approximately 30% of the numbers began with the digit 1. About 18% began with 2. 12.5% began with 3. The frequency continued to decline through the higher digits, with 9 appearing as the first digit less than 5% of the time. To take one specific example from his data, when Benford examined the 308 numbers appearing in that issue of Reader's Digest, he found that 33.4% began with 1, 18.5% began with 2, and 12.4% began with 3. The pattern wasn't perfect, but the general trend was unmistakable. Lower digits dominated, higher digits were scarce. Benford published his findings in the Proceedings of the American Philosophical Society in an article titled The Law of Anomalous Numbers. The name itself captured the strangeness of what he had found. These weren't random numbers or artificial constructions. These were numbers that arose from counting and measuring real things in the real world. And yet they behaved anomalously, defying the expectation of equal distribution across all digits. The phenomenon Benford documented extended beyond first digits. He found that second, third, and subsequent digits also followed predictable patterns, though the distributions became more uniform as you moved further into the number. The combination of first and second digits, or first, second, and third digits, also adhered to precise logarithmic distributions. For instance, numbers beginning with the two-digit combination 1-4 should appear with a specific calculable probability, as should numbers beginning with 3-1-4, and so on, through all possible combinations.
The pattern held regardless of whether measurements were taken in different units, a property that would prove central to understanding why the law works. It appeared in mathematical sequences as well. Take the sequence of powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, and so on. In the first 96 numbers of this sequence, the digit 1 appears as the leading digit 29 times, or 30.2% of the time. The digit 2 appears 17 times, or 17.7%. These percentages align almost perfectly with the predicted distribution. The sequence follows a geometric progression, and geometric progressions naturally generate numbers that conform to this logarithmic pattern of first digits. Benford's law applies to the populations of countries. When you list the populations of the world's nations, about 30% begin with 1, meaning their populations fall somewhere between 1 million and 2 million, or between 10 million and 20 million, or between 100 million and 200 million. The distribution of first digits in country populations produces a chart that follows the now familiar downward curve from 1 to 9.
Yet the law doesn't apply universally, and recognizing when it fails to apply is as important as recognizing when it succeeds. Human heights, when measured in feet, don't follow Benford's law at all. Nearly all adult heights begin with 4, 5, or 6 feet. The digits 1, 2, 3, 7, 8, and 9 simply don't appear as leading digits in this data set because human physiology constrains height to a narrow range. The data span less than one order of magnitude, and Benford's law requires data that spread across multiple orders of magnitude to manifest clearly. Similarly, a list of invoice amounts from a company that charges either $49.99 or $79.99 for its products won't follow the law. The digits 4 and 7, or possibly 5 and 8 if sales tax is included, will appear as leading digits far more frequently than the law predicts, because the data generation process is artificially constrained. Assigned numbers like telephone numbers, social security numbers, and zip codes don't follow the pattern either, because these numbers aren't measuring natural quantities. They're labels assigned according to administrative systems. IQ scores provide another example of data that won't conform. IQ tests are designed to produce scores that cluster around 100, with a standard deviation of 15. The vast majority of scores, therefore, begin with the digit 1, not because of any logarithmic law, but because the test is intentionally constructed to produce that result. The data don't span multiple orders of magnitude, and they arise from an artificial process rather than from measuring diverse natural phenomena.
The counterintuitive nature of Benford's discovery lies precisely in this tension. Our intuition tells us that digits should appear equally in random collections of numbers. When we make up numbers or assign them artificially, we tend to distribute the digits fairly evenly because that feels random. But genuine data from natural processes, from phenomena that grow and evolve and interact across different scales, don't distribute their digits evenly. They concentrate heavily on the lower digits, creating that characteristic steep decline from 1 to 9. Benford noted in his original paper that while individual data sets might show some deviation from the predicted distribution due to random variation or specific characteristics of the phenomenon being measured, the mean of many diverse data sets should conform closely to the law. The pattern wasn't a statement about any single type of number or measurement, but rather a statement about the collective behavior of numbers arising from heterogeneous natural processes. The rediscovery and popularization of this pattern through Benford's work raised profound questions. Decades later, researchers would discover that this mathematical signature could detect fabricated data, since numbers invented by humans don't naturally follow the logarithmic distribution. The applications would prove revolutionary, from corporate fraud detection to election forensics to validation of scientific research. But before the pattern could be applied, a deeper mystery demanded resolution. Why does the universe favor smaller leading digits at all? The answer would lie in fundamental properties of logarithms, scale, and the nature of measurement itself. Chapter 2. The Mathematical Mystery of Scale Invariance and Why the Universe Inherently Favors Smaller Leading Digits. When Frank Benford examined the heights of the world's tallest structures, he made a curious discovery that went beyond the simple observation that more buildings began with the digit 1 than with 9. He found that the pattern persisted regardless of whether he measured the structures in meters or in feet. 23 of the 58 tallest structures had heights beginning with 1 when measured in meters, while 15 began with 1 when measured in feet. The percentages differed slightly, but both hovered near the predicted 30%. This wasn't a coincidence or an artifact of choosing convenient units. It was a fundamental property of the distribution itself, one that would prove central to understanding why Benford's law works at all. Consider what this means. A building that stands 322 meters tall measures 1,057 feet. In meters, the first digit is 3. In feet, the first digit is 1. Yet somehow, when you examine all tall structures collectively and count first digits in meters, then count them again in feet, both counts produce approximately the same logarithmic distribution. The law doesn't care whether you measure in meters, feet, furlongs, or any other unit. This property is called scale invariance, and it's the key to unlocking the mathematical mystery of why the universe appears to favor smaller leading digits. Imagine you have a data set of river lengths that conforms to Benford's law when measured in kilometers. Now convert every length to miles by multiplying by 0.621371. Some rivers that began with the digit 1 in kilometers will now begin with different digits in miles, and vice versa. Yet when you count up all the first digits in the converted data set, you'll find they still follow the same logarithmic pattern. The distribution is invariant under scaling, meaning it remains unchanged when you multiply all the numbers by a constant factor. This scale invariance is not just a curious mathematical property, it's actually a defining characteristic of Benford's law. In fact, researchers have proven that Benford's distribution is the only probability distribution for first digits that possesses this scale invariance property. If you want a distribution of leading digits that doesn't change when you change units, you must have Benford's law. No other distribution will work. To understand why, we need to shift our perspective from thinking about the numbers themselves to thinking about their logarithms. When Newcomb first articulated his discovery, he stated that all mantissae of logarithms are equally probable. This statement, which might seem abstract or overly technical, contains the entire mathematical foundation of the law. The mantissa is the fractional part of a logarithm. If you take the base 10 logarithm of 1701.24601, you get 3.230671 approximately. The integer part, 3, is called the characteristic. The decimal part, 0.230671, is the mantissa. Newcomb's claim that mantissae are uniformly distributed means that this fractional part of the logarithm is equally likely to fall anywhere between 0 and 1.
If you were to plot the mantisae of all numbers in a dataset on a number line from 0 to 1, they should be spread out evenly with no clustering or gaps. This uniform distribution of mantisae directly produces the logarithmic distribution of first digits. Here's how it works. A number has a first digit of 1 if and only if its significand lies between 1 and 2. The significand is the number expressed in scientific notation with the decimal point placed immediately after the first non-zero digit. For instance, the significand of 1701.246 is 1.701246. The significand of 0.02092 is 2.092. Both numbers are scaled to lie in the range from 1 up to but not including 10. When you take the base 10 logarithm of a number with significand between 1 and 2, you get a value whose mantissa falls between 0 and logarithm of 2. The logarithm of 1 is 0, and the logarithm of 2 is approximately 0.3010. So numbers with first digit 1 correspond to mantissae in the range from 0 to 0.3010. Similarly, numbers with first digit 2 correspond to mantissae between logarithm of 2 and logarithm of 3, which is the range from approximately 0.3010 to 0.4771. Numbers with first digit 9 correspond to mantissae between logarithm of 9 and logarithm of 10, which is the narrow range from approximately 0.9542 to 1.000. If the mantissae are uniformly distributed between 0 and 1, then the probability of observing a particular first digit equals the length of the corresponding interval. The interval for first digit 1 spans from 0 to 0.3010, a length of 30.1%. The interval for first digit 2 spans from 0.3010 to 0.4771, a length of 17.6%. The interval for first digit 9 spans from 0.9542 to 1.0, a length of only 4.6%. The intervals grow progressively narrower as the first digit increases, producing exactly the distribution Benford observed. You can visualize this most clearly by imagining a logarithmic scale, like the kind found on slide rules that engineers used before calculators became common. On a logarithmic scale, the distance from 1 to 2 is much greater than the distance from 9 to 10, even though both represent an increase of 1 in absolute terms. This is because on a logarithmic scale, equal distances represent equal ratios rather than equal differences. The ratio from 1 to 2 is 2 to 1, a doubling. The ratio from 9 to 10 is 10 to 9, only an 11% increase. If you were to throw a dart at a logarithmic number line spanning from 1 to 10, and the dart had an equal probability of landing anywhere along the physical length of that line, it would be much more likely to land in the region between 1 and 2 than in the region between 9 and 10, simply because the 1 to 2 region takes up more physical space. This geometric fact translates directly into the probability distribution of first digits when logarithms are uniformly distributed. The scale invariance property now becomes clear. When you multiply all numbers in a dataset by a constant, you're shifting all the logarithms by the same amount. Specifically, multiplying by a factor of k adds logarithm of k to every logarithm. Adding a constant to a uniformly distributed variable simply shifts the distribution without changing its uniformity. The mantissae remain uniformly distributed between 0 and 1, though individual values shift and wrap around when they exceed 1. Because the distribution of mantissae stays uniform, the distribution of first digits stays the same. This is profoundly different from what happens with most distributions. If you have a normal distribution of heights in meters and convert them to feet, the shape of the distribution changes. The peak shifts, the spread changes. But Benford's law is immune to such transformations because it's fundamentally a statement about logarithmic space rather than linear space. Benford's law also exhibits base invariance, meaning it works not just in base 10, but in any integer base. In binary, base 2, every positive number can be expressed with just the digits 0 and 1. Benford's law in binary is trivial for first digits because every number except 0 begins with 1.
But even in binary, the law makes non-trivial predictions for second and later digits. In base 3, using digits 0, 1, and 2, Benford's law predicts the probability of first digit 1 is logarithm base 3 of 2, approximately 63%, while the probability of first digit 2 is logarithm base 3 of 3 minus logarithm base 3 of 2, approximately 37%. The general formula for any base b greater than or equal to 2 states that the probability a number begins with digit d equals logarithm base b of 1 plus 1 over d. This formula encompasses the base 10 version as a special case. The fact that the same mathematical principle applies across all bases suggests something fundamental about positional number systems themselves, not just about the decimal system we happen to use. Why should mantisae be uniformly distributed in naturally occurring data? This question puzzled researchers for decades. The answer lies in the processes that generate most real-world numbers. Many natural phenomena grow or shrink through multiplication rather than addition. Populations grow by a certain percentage each year. Investment returns compound. Radioactive substances decay by a constant fraction per unit time. Whenever you have a process involving repeated multiplication by varying factors, you're essentially adding logarithms repeatedly, and this leads to a spreading out of the logarithmic values. Consider a stock price that begins at $100. Each day, the price changes by some random percentage, up or down. After one day, it might be at $101 or $99. After a week, after a month, after a year, the price has wandered through a multiplicative random walk. The logarithm of the stock price is undergoing an additive random walk, since the logarithm of a product equals the sum of the logarithms. As this process continues over extended time, the central limit theorem from probability theory suggests that the distribution of the logarithm becomes increasingly broad and smooth, eventually spreading across many orders of magnitude in an approximately uniform way. This is why Benford's law applies most reliably to data sets spanning several orders of magnitude. If your data ranges from 10 to 100, it covers just one order of magnitude, and the distribution of logarithms doesn't have enough room to spread out uniformly. But if your data ranges from 1 to 10,000, spanning 4 orders of magnitude, the logarithms range from 0 to 4, giving ample room for approximate uniformity to develop in the fractional parts. The connection to orders of magnitude also explains why additive processes don't typically generate Benford-distributed data. If you're measuring phenomena that grow through addition rather than multiplication, such as the sum of many small independent contributions, the central limit theorem tells you the result will approximate a normal distribution. Normal distributions are concentrated around a mean value and don't spread across many orders of magnitude. Heights, weights, test scores, and similar quantities produced by additive processes tend to cluster within one order of magnitude and thus don't conform to Benford's law. Another way to understand the prevalence of smaller leading digits is through the concept of scale crossing. Imagine counting upward from 1. To get from 1 to 2, you must count 1, then 2. To get from 10 to 20, you count 10, 11, 12, and so on through 19 before reaching 20. To get from 100 to 200, you count 100, 101, 102, continuing through all 100 numbers in the 100s before entering the 200s. At every scale, every order of magnitude, you spend more time in the low digits than in the high digits, simply because that's where counting begins at that scale. Now imagine a quantity that grows continuously, like a population or a bank balance. As it grows from 1,000 to 10,000, it spends time at every value in between. It enters the 1,000s, passes through the entire range of 1,000 to 2,000, then enters the 2,000s and passes through 2,000 to 3,000, and so on. The time spent in the 1,000s, where the first digit is 1, equals the time it takes to grow from 1,000 to 2,000. If growth is proportional to current size, as it is in exponential growth, this is a doubling, taking the same amount of time regardless of the starting value. The time spent in the 9,000s, where the first digit is 9, equals the time to grow from 9,000 to 10,000, which is only an 11% increase and thus takes much less time. This temporal argument applies even to non-temporal quantities. Any process that generates numbers through stages, where progression through the stages follows a roughly geometric pattern, will naturally spend more time or more probability mass in the regions corresponding to lower first digits. The mathematics of logarithms ensures this outcome.
The distribution also arises from combinations of different data sources. Theodore Hill proved that if you randomly select numbers from randomly selected probability distributions, the resulting collection of numbers tends toward Benford's law. This distribution of distributions principle helps explain why data compiled from diverse sources, like the numbers in a magazine or newspaper, often conform to the law even though no single generating process produced them. Each article might discuss different types of quantities measured on different scales. But when you pool all these numbers together, their first digits aggregate into the characteristic logarithmic pattern. Interestingly, the distribution is robust to certain types of transformations beyond simple scaling. Taking a collection of Benford distributed numbers and multiplying each one by a different randomly chosen factor tends to preserve the Benford property. Raising Benford distributed numbers to various powers often maintains the distribution. This robustness means that if a natural phenomenon involves combining or transforming quantities that individually follow Benford's law, the result will also follow the law. The distribution propagates through calculations, maintaining its signature even as numbers undergo complex manipulations.
All of this mathematical machinery points to a surprising conclusion about the nature of measurement and number. The distribution of first digits isn't an arbitrary property of the things being measured. It's a consequence of how measurement works when applied across varying scales, how multiplication operates, how geometric growth proceeds, and how positional number systems represent quantities. The universe doesn't favor smaller leading digits in the sense of having a preference. Rather, the mathematics of combining, growing, and representing quantities naturally concentrates probability density in the regions corresponding to lower first digits when the underlying processes operate multiplicatively across multiple scales of magnitude. This realization transforms Benford's law from a curious empirical observation into a deep statement about structure. It's not merely a pattern someone noticed in data tables. It's a mathematical necessity that emerges from the interplay of logarithms, probability, and positional notation. Any alien civilization using a positional number system and studying multiplicative processes in nature should discover the identical distribution, scaled to whatever base they happen to use for their arithmetic. Given this mathematical foundation, a provocative question emerges. If naturally occurring numbers conform to this precise logarithmic distribution as a consequence of how they're generated and represented, what happens when numbers don't occur naturally but are instead fabricated by someone trying to commit fraud?
Chapter 3. From Mathematical Curiosity to Forensic Weapon. The mathematical elegance of Benford's law might have remained a curiosity confined to academic journals if not for a simple but powerful insight that emerged in 1972. An economist named Hal Varian published a brief letter suggesting that if naturally occurring numbers follow a predictable logarithmic pattern, then fabricated numbers probably don't. His reasoning was straightforward. When people invent numbers, they tend to distribute digits fairly uniformly because that's what feels random to the human mind. We instinctively avoid patterns, seeking to make our fabrications appear unbiased. But this very instinct betrays us. True randomness in naturally occurring data isn't uniform at all. It concentrates heavily on the lower digits. A simple comparison between the expected Benford distribution and the actual distribution in a data set could therefore reveal whether someone had manipulated the figures. Variance proposal targeted socioeconomic data submitted to support public planning decisions. Government officials and private interests frequently provided statistics to justify funding requests, zoning changes, or regulatory decisions. These numbers carried enormous weight in policymaking, yet they were difficult to verify independently. Auditors couldn't easily check whether every submitted population figure, economic projection, or impact assessment reflected reality. But they could count the first digits. If a data submission claimed to contain thousands of genuine measurements, yet showed an implausible distribution of leading digits, something warranted closer scrutiny. The concept languished for 2 decades before someone developed it into a practical tool. In 1992, an accountant named Mark Negrini completed a doctoral dissertation proposing the use of Benford's law to detect fraudulent tax returns. Negrini recognized that tax data possessed exactly the characteristics that made Benford's law applicable. Income figures, deductions, business expenses, and reported revenues spanned multiple orders of magnitude. A return might include deductions ranging from tens of dollars to tens of thousands. These numbers arose from genuine economic activity, from transactions recorded throughout a tax year. If the data were authentic, the first digits should follow the logarithmic distribution. If someone had fabricated deductions or inflated expenses, the digits would likely show a different pattern. Negrini's innovation extended beyond simply proposing Benford's law as a fraud detection tool. He developed comprehensive testing protocols that examined not just first digits, but second digits, combinations of first and second digits, and even patterns in the final 2 digits of numbers. He recognized that sophisticated fraudsters might learn to manipulate first digits to match Benford's distribution while neglecting subsequent digits. His methodology called for chi-squared statistical tests with 8 degrees of freedom and a critical value of 15.507 at the 0.05 significance level to assess conformity. These technical specifications gave auditors and investigators concrete thresholds for deciding when deviations warranted further investigation. The practical implementation that Negrini championed made the technique accessible to working accountants and auditors. He provided detailed instructions for applying Benford analysis using standard spreadsheet software. An auditor could extract a column of financial data, use the left function to isolate the first digit of each number, employ the COUNTIF function to tally how many times each digit appeared, and generate a column chart comparing the observed frequencies to the expected Benford distribution. This democratization of the technique meant that fraud detection through digit analysis no longer required specialized statistical software or advanced mathematical training. Any competent accountant with basic spreadsheet skills could deploy the method. The International Revenue Service began incorporating Benford analysis into audit selection procedures in the mid-1990s. The method offered an efficient screening mechanism that could process thousands of returns through a computerized Benford test in minutes. Examiners could flag returns with unusual digit patterns for closer examination. This didn't prove fraud. An anomalous distribution might have innocent explanations, from data entry errors to legitimate peculiarities in a particular business sector. But it provided a reason to look more carefully, a quantitative justification for deploying limited audit resources toward returns that statistically deserved scrutiny. The application to tax enforcement revealed a critical psychological dimension to the law. When people fabricate financial data, they make predictable mistakes. Someone inventing deductible expenses tends to avoid round numbers, correctly reasoning that a string of expenses ending in exactly $0 looks suspicious. They sprinkle in varied amounts, perhaps claiming deductions of $1,873, $2,219, $4,567. These amounts feel random, and the variance in the final digits provides a patina of authenticity. But the person choosing these numbers unconsciously spreads the first digits more evenly than nature does. They'll generate too many amounts beginning with 7, 8, and 9, and too few beginning with 1. Their attempt to appear random reveals itself through violation of Benford's law. Research into the psychology of numerical fabrication confirmed this pattern. When experimental subjects were asked to invent data sets of financial transactions, they consistently produced distributions that deviated from Benford's law in characteristic ways. They matched the first-digit distribution reasonably well, suggesting some intuitive awareness of the pattern, but failed dramatically when it came to second digits and digit combinations. Their fabrications also showed anomalous patterns in final digits. Genuine transaction amounts tend to cluster at certain endings based on pricing strategies and rounding, but fabricated amounts showed either excessive uniformity across all possible endings or implausible concentrations at specific values the fabricator favored.
This same principle extended across diverse fraud detection domains. Corporate accounting fraud became a major application area, though not through simple application to entire general ledgers. Forensic accountants developed sophisticated protocols for deploying Benford analysis to minimize false positives while maximizing detection of genuine anomalies. They learned to segment data carefully before applying the test. A company with multiple divisions operating in different markets might show unusual digit distributions if all the data were analyzed together, even without any fraud, because different divisions operated at different scales. Proper application required examining each division separately or grouping similar transactions. They learned to consider the business context meticulously. A rental car company that charged standardized daily rates might legitimately show more instances of specific first digits because the rates themselves didn't vary much. A construction firm with many contracts at similar sizes would naturally produce clustering in certain digit ranges. An insurance company processing mostly small claims under certain coverage limits would generate data confined within narrow bounds that might not span enough orders of magnitude for Benford's law to apply meaningfully. Without deep knowledge of the business model and industry norms, an analyst might flag legitimate data as suspicious based solely on digit distributions. Practitioners developed a hierarchy of responses to observe deviations. A slight departure from the expected distribution might warrant only a note for future reference. A moderate deviation might trigger additional analytical tests, such as examining second digits or looking at digit combinations. A severe deviation would justify allocating investigative resources to examine the underlying transactions. No competent auditor would conclude fraud based solely on a Benford test, but many competent auditors began investigations based on anomalies the test revealed. The method proved particularly effective for invoice number fraud. Invoice numbers obey Benford's law when a company issues invoices continuously over time, with the numbering sequence growing from hundreds to thousands to tens of thousands. The probability that an invoice number starts with either a 1 or a 2 equals 0.477, nearly half. An employee creating fictitious vendors and submitting fake invoices for payment would need to invent plausible-looking invoice numbers. If they generated these numbers without regard for Benford's law, their fabricated invoice numbers would show anomalous digit patterns that could flag the fraud scheme for investigation. Election forensics became another application domain, though one fraught with methodological challenges. Vote counts from precincts, particularly in countries where precinct sizes vary widely, can span multiple orders of magnitude and might conform to Benford's law when genuinely tabulated. The development of electoral Benford analysis as a legitimate forensic technique created tools for examining contested elections where direct access to ballots and counting processes was impossible. The application of Benford's law to elections revealed significant pitfalls that required careful methodological attention. In the aftermath of the 2020 United States presidential election, claims circulated on social media asserting that vote counts in certain cities violated Benford's law, supposedly proving fraud. These claims focused on counties where one candidate received strong support, particularly in urban areas of swing states. Charts appeared showing that the first digits of precinct-level vote totals didn't match the expected Benford distribution, which was presented as evidence of manipulation. The problem was that these analyses fundamentally misapplied the law.
Precinct-level vote counts in American elections typically range from a few dozen votes to a few thousand. They don't span multiple orders of magnitude. They're bounded by the physical capacity of polling places and the administrative structure of voting districts. Benford's law requires data that's spread across many orders of magnitude to produce the characteristic distribution. When applied to data confined within a narrow range, the law simply doesn't hold, and deviations from the predicted distribution are expected and meaningless. Walter Maybain, a political scientist who had pioneered legitimate applications of statistical forensics to elections, explicitly addressed the misuse of the method in the 2020 American election context. He stated unequivocally that first digits of precinct vote counts are not useful for diagnosing election frauds. The misapplication demonstrated a crucial lesson. Benford's law is a powerful analytical tool when applied to appropriate data under appropriate conditions. Applied inappropriately, it generates misleading results that can be weaponized to spread disinformation. The criminal justice system gradually accepted Benford analysis as admissible evidence in fraud trials. In the United States, courts at federal, state, and local levels heard testimony from expert witnesses explaining the mathematical foundations of the law and its forensic applications. The case of Wesley Rhodes illustrated this evolution. Rhodes operated as a financial advisor and was accused of defrauding investors by fabricating account statements and investment returns. Prosecutors argued that Rhodes's documents failed to conform to Benford's law, suggesting the numbers had been manufactured rather than representing actual transactions. The statistical evidence formed part of the prosecution's case, and Rhodes was ultimately convicted. The court's acceptance of Benford analysis as legitimate forensic evidence represented a significant milestone in the law's journey from mathematical oddity to practical investigative tool. The legal framework for admissibility required that expert witnesses establish the scientific validity of Benford's law, explain why it applied to the specific type of data in question, demonstrate that proper protocols had been followed in conducting the analysis, and acknowledge the limitations and alternative explanations for observed deviations. Courts recognized that Benford analysis alone didn't prove fraud, but could constitute probative evidence when combined with other investigative findings. Defense attorneys learned to challenge Benford evidence by questioning whether the data met the preconditions for the law's application, whether the analysis had been conducted properly, and whether innocent explanations could account for the observed patterns. The intersection of Benford's law with consumer pricing revealed unexpected applications. Researchers studying price data across European markets examined whether merchants used psychological pricing strategies. Psychological pricing involves setting prices just below round numbers, such as charging $9.99 instead of $10 to make items appear less expensive than they are. The hypothesis was that if prices were set naturally based on costs and competitive factors, they should follow Benford's law. If prices showed anomalous concentrations of certain digits, it would indicate strategic pricing manipulation. The researchers examined consumer product prices before and after the introduction of the euro in 2002. Before the euro, when each European country had its own currency, prices in any given country were expressed in that country's traditional units. After the euro's introduction, prices across the eurozone were expressed in a common currency. During the transition period, merchants couldn't simultaneously employ psychological pricing in both the old local currency and the new euro. A price that ended in 99 cents in euros wouldn't necessarily end in 99 cents when converted to the old currency at the official exchange rate. The study found that first-digit distributions in prices followed Benford's law reasonably well, but second- and third-digit distributions showed significant deviations before the euro's introduction, then moved closer to Benford predictions during the transition, and then deviated again after consumers adapted to thinking in euros. This pattern confirmed that merchants actively manipulated prices in ways that violated the natural distribution of digits, and that they suspended this manipulation when the currency change made it impractical, only to resume once the new currency became psychologically established.
Scientific research itself became subject to Benford scrutiny. Researchers analyzing published regression coefficients in academic papers found that genuine results adhered to Benford's law, while fabricated statistics did not. When subjects were asked to invent statistical estimates rather than deriving them from actual data, their fabrications matched Benford's distribution for first digits, suggesting the participants had some awareness of the expected pattern, but failed to match the distribution for second digits, revealing their deception. This application raised uncomfortable questions about the integrity of published research across scientific disciplines, and provided journal editors and peer reviewers with a potential tool for flagging suspicious data sets that might warrant additional scrutiny before publication. The expanding use of Benford's law as a fraud detection tool created a cat-and-mouse dynamic. As awareness of the law spread, sophisticated fraudsters might learn to manufacture data that deliberately conformed to the expected distribution. This possibility led some experts to question whether the technique would remain effective as knowledge of it became widespread. Others argued that generating convincingly Benford-compliant fake data required more sophistication than most fraudsters possessed. The psychological tendency to perceive uniform digit distributions as random appeared deeply ingrained, and even people who intellectually understood Benford's law often failed to internalize it when fabricating numbers under pressure.
Moreover, matching the first digit distribution was only the beginning. Benford's law makes specific predictions about second digits, third digits, combinations of digits, and the distribution of final digits as well. An analysis could examine dozens of different statistical properties of a data set. Fabricating data that passed all these tests simultaneously while also maintaining internal consistency, telling a coherent story, and matching expected patterns in related variables would require remarkable skill and attention to detail. Most fraud involved opportunistic manipulation by individuals who weren't statisticians and who wouldn't anticipate multi-layered digit analysis. The limitations and appropriate scope of Benford's law as a fraud detection technique remain subjects of active debate among forensic accountants, auditors, and statisticians. The method worked best as a first-line screening tool that could process vast quantities of data quickly and highlight areas deserving closer inspection. It proved less effective as standalone proof of wrongdoing. Deviations from Benford's distribution didn't constitute definitive evidence of fraud, and conformity to the distribution didn't prove data integrity. The technique identified data sets that warranted investigation, but couldn't replace that investigation.
Certain types of data simply didn't conform to Benford's law regardless of their authenticity. Any dataset confined to a narrow range of values, such as human heights measured in feet, adult ages in years, or standardized test scores, would violate the distribution through no fault of dishonesty. Data generated by additive rather than multiplicative processes, such as the sum of many small independent transactions, tended toward normal distributions that didn't match Benford's predictions. Assigned numbers like telephone numbers, account numbers, or identification codes bore no relation to Benford's law because they weren't measuring natural quantities. Yet the fundamental insight that authentic, naturally occurring data possessed a distinctive statistical signature that fabricated data lacked proved robust across diverse domains. Whether examining corporate ledgers, tax returns, scientific measurements, or economic statistics, the logarithmic distribution of leading digits provided a mathematical benchmark against which submitted data could be measured. Deviations from that benchmark didn't constitute proof of wrongdoing, but they raised questions that warranted answers.
The transformation of Benford's law from Newcomb's observation about Warren logarithm tables into a practical investigative tool deployed by tax agencies, corporate auditors, forensic accountants, and fraud investigators worldwide represented one of the more unusual journeys in applied mathematics. A pattern noticed in the physical wear of reference books became a weapon against financial crime, tax evasion, and data manipulation.
Whether that weapon would remain sharp as knowledge of it spread, and whether wielding it responsibly required more judgment than many practitioners possessed, were questions that would be tested in high-stakes cases where billions of dollars, political legitimacy, and human freedom hung in the balance. Chapter 4. 3 Controversial Applications. The mathematics underlying Benford's law are settled science, but its application to real-world accusations of fraud has never been simple or uncontroversial. When statisticians point to digit distributions and declare that data have likely been fabricated, they enter territory where mathematics intersects with politics, law, economics, and human reputations. 3 major case studies illustrate both the power and the peril of deploying Benford's law in high-stakes investigations, where billions of dollars, political legitimacy, and national sovereignty hang in the balance. The Iranian presidential election of June 2009 became the most internationally visible test case for electoral Benford analysis. When the Interior Ministry announced results showing incumbent President Mahmoud Ahmadinejad winning with over 63% of the vote, carrying even districts where his opponent Mir Hossein Mousavi had strong historical support, massive street protests erupted in Tehran. The government controlled the ballots, the counting process, and access to polling stations. International observers had been denied entry. Under these circumstances, independent verification appeared impossible, creating exactly the situation where statistical forensics could provide otherwise unavailable evidence. Walter Meebane's analysis of the reported vote counts revealed significant deviations from the expected second-digit distribution in Ahmadinejad's totals. More tellingly, he found a correlation between ballot boxes reporting very few invalid ballots and disproportionate tallies favoring Ahmadinejad. This pattern suggested ballot stuffing. In genuine elections, a certain percentage of ballots are inevitably spoiled through voter error. When a ballot box reports almost no invalid ballots, yet contains hundreds of valid votes, it raises suspicion that someone added pre-marked ballots. Other research teams approached the data from different angles. One group found that Mehdi Karoubi's vote totals began with the digit 7 approximately twice as often as Benford's law predicted, a glaring anomaly. The Columbia University team identified what they called too few non-adjacent digits in the reported results, calculating that the probability of all these anomalies appearing together in a fair election was less than half of 1%. These statistical findings generated international headlines and provided quantitative ammunition to those denouncing the election as fraudulent. But the Iranian government rejected the analyses entirely, dismissing them as Western propaganda. Officials argued that American and European statisticians had no credibility to judge Iranian elections, and that the mathematical methods were being weaponized for political purposes. This political context highlighted a fundamental tension. When statisticians from countries hostile to a particular government announce that its election results appear fraudulent based on digit distributions, how should that evidence be weighted? Critics also pointed out genuine methodological concerns. Benford's law requires data spanning multiple orders of magnitude. Do election vote counts meet these criteria? Vote counts from large cities might range from dozens to tens of thousands across different polling places. But in more homogeneous districts, vote totals might cluster within a narrower range that doesn't satisfy the law's preconditions. The application of Benford's law to corporate fraud presented different challenges, though ones less politically charged than electoral forensics. The Enron scandal of 2001 exposed massive accounting fraud at what had been one of America's largest companies. Executives had used complex special-purpose entities to hide billions in debt and inflate billions in profit. When the scheme collapsed, thousands of employees lost their jobs and retirement savings, while shareholders saw their investments evaporate. Forensic accountants examining Enron's financial records during 2002 extracted datasets from the company's general ledger and accounts payable systems, focusing particularly on the quarters when fraud was most intensive.
Analysis of transactions in Enron's wholesale energy trading division revealed that expenses recorded in accounts tied to certain special-purpose entities showed unusual concentrations of amounts beginning with the digits 5 and 7. In one analysis of approximately 8,000 transactions across suspect accounts, first digits 5 and 7 appeared at combined frequencies exceeding 35%, nearly double their expected probability under Benford's law. The analysts also found anomalies in the company's reserve accounts, where management had discretion to record estimates for future liabilities. Reserves that should have reflected diverse underlying obligations instead showed suspicious clustering in their leading digits. One set of quarterly adjustments to derivatives valuations contained 42 entries beginning with 4, 17 beginning with 7, and only 11 beginning with 1, an inversion of the expected pattern so severe that it warranted immediate investigation of the specific transactions.
These digit distribution patterns didn't prove fraud by themselves. Enron was a genuine operating company conducting real business even while executives manipulated the books. Many numbers in Enron systems reflected authentic transactions, and the fraudulent entries were interspersed among legitimate ones. Investigators needed other evidence pointing them toward particular suspicious areas before Benford analysis could confirm those suspicions. The Securities and Exchange Commission had already identified problematic special-purpose entities through tips from former employees and analysis of disclosure documents. The digit tests helped prioritize which of thousands of accounts deserved intensive scrutiny and provided quantitative justification for allocating investigative resources. What made the Enron case significant was how it demonstrated Benford analysis functioning within a comprehensive forensic toolkit. Prosecutors ultimately convicted several top executives based on evidence that included testimony from cooperating witnesses, internal emails revealing fraudulent intent, analysis of complex financial structures, and yes, statistical anomalies in the accounting records. The mathematical patterns couldn't stand alone, but they guided investigators through an overwhelming volume of data to find specific transactions that human judgment could then evaluate for criminal intent.
The revelation in 2009 that Greece had manipulated its macroeconomic statistics to gain entry to the European Union's Eurozone illustrated Benford's law operating at the level of national accounts. Joining the Eurozone required meeting strict fiscal criteria, budget deficits below 3% of gross domestic product, and public debt below 60% of GDP. Greece's actual fiscal position didn't meet these requirements. Government officials working with investment banks employed creative accounting to hide the true extent of Greece's borrowing. They used currency swaps and other derivative instruments to move debt off the government's balance sheet temporarily. When a new government revealed in 2009 that previous administrations had systematically falsified the statistics, the scale of the deception became clear. Greece's actual deficit in 2009 was 15.4% of GDP, not the 3.7% initially reported. Debt ratios that Greece had reported as hovering near the 60% threshold were actually above 100%. Researchers subsequently applied Benford's law to the historical macroeconomic data Greece had submitted to European authorities between 1999 and 2003. The analysis found significant deviations from the expected logarithmic distribution in reported budget figures, GDP components, and debt statistics. Government expenditure data showed excessive concentration of first digits 8 and 9 during the critical application period, precisely the pattern one would expect if officials were inflating numbers that naturally clustered at lower values to push them above reporting thresholds. The Benford test, applied retrospectively, flagged the very data sets later proven to have been manipulated. This created an uncomfortable realization. The tools to detect this fraud existed when the data were submitted, but no one applied them. The European institutions responsible for vetting member state statistics relied on trusting that governments reported honestly. They conducted audits of statistical methodologies, but apparently didn't run basic fraud detection tests on the numbers themselves.
The question of whether international organizations should routinely apply Benford tests to submitted data remains unresolved, raising tensions between diplomatic courtesy to sovereign governments and responsibility to validate information that affects billions in financial commitments. In all three cases, Iranian elections, Enron, and Greek statistics, Benford's law provided quantitative support for suspicions arising from other sources rather than establishing fraud definitively on its own. The digit anomalies were most powerful when combined with eyewitness accounts, whistleblower testimony, investigative journalism, or subsequent admissions. Whether these statistical patterns should carry evidentiary weight in courts, inform international policy decisions, or shape public opinion about electoral legitimacy remained contested, revealing that translating mathematical probability into conclusions about human behavior requires judgment that extends well beyond the formulas themselves.
Benford's law reveals something profound about the universe we inhabit. What began as a curiosity noticed in worn logarithm tables became a window into the fundamental mathematics of scale, measurement, and naturally occurring phenomena. The logarithmic distribution of first digits isn't arbitrary. It's a mathematical necessity arising from how quantities grow, combine, and span multiple orders of magnitude. Yet, as we've seen, translating mathematical certainty into conclusions about human behavior requires careful judgment. Benford's law is a powerful tool for detecting anomalies, but it cannot stand alone as proof. It flags what deserves investigation, not what constitutes guilt. The same pattern that helps auditors find fraudulent tax returns can be misapplied to spread election disinformation. Perhaps the deepest lesson is this: nature speaks in mathematical patterns that humans struggle to replicate when we fabricate data. Our intuitions about randomness betray us, revealing the distance between what feels random and what actually is. Thank you for listening.